At long last, we're back to Hollywood. From now on, class videos for our present gathering will be available at Absolutely Chemistry. So if nothing else, if during a particular lecture presentation you miss something, go look at it again. It's there. On occasion, students have asked me for permission to record the class. Hey, be my guest, but we're recording it for you. So you shouldn't have to do that. But if you wish, I don't mind. Here is our present out-of-class help schedule. CLC is Flynn 257, which the syllabus tells you. And again, I say to you, if you find that you need out-of-class assistance to keep pace with our gathering, and I know some of you will, go get the assistance as soon as you need it. Don't wait for this stuff to pile up, because it's going to get thicker and more detailed as we proceed. And you will also see, which I have reminded you about, at least to some extent, as we go further, the stuff we do in the future will depend on what we are doing presently. I don't know what's going on in 2045, but in science, you have to perpetually build foundation as you move to higher and deeper levels of understanding, which means what you learn on the first day must always be with you, so that you can use it as necessary to support what you're going to learn on the second day. And then day 1 and day 2 have to be with you to get at day 3 and stuff like that. It's like in math class. You think you can succeed in Calc 1 if you don't know how to do algebra? Well, you can try. I don't know how you'd fare, but you can try. I don't recommend that method of operation. Again, these are the names for our 4 discussion class instructors, and these are the people that you want to see, me included, when you seek out-of-class assistance. This is all posted to Sakai. My office time is in our syllabus, and my office time is also included in the Sakai posted out-of-class help schedule. Equilibrium continued. We talked last time about fundamental considerations which underlie your success in doing equilibrium calculations. Now, we'll take a look at a couple of equilibrium systems which are considered in Chem Notes 2, including challenge problem 17.1, which again will be the nitrogen-hydrogen-ammonia equilibrium system, which we'll look at in detail, in particular to give you an idea of the considerations that you must be on top of, must be aware of, to deal with equilibrium calculations successfully for any equilibrium system. But back first to page 1717 and 1718, where this rather simple gas phase equilibrium system is being considered. Well, we can look at it from a left to right reaction standpoint or from an equilibrium standpoint. Question. This question is based on your having read the stuff in the notes which leads up to this. Because I take it for granted that you do these things without my having to tell you. If this system is alive and well in a piston cylinder gadget, and you apply pressure to the system, or reduce the pressure on the system, you can take a hold of the handle on the piston, push it into the cylinder, increase pressure, reduce the volume, or you can take a hold of the handle on the piston and pull it out, not totally out, so as to reduce pressure and increase the volume of the system. Will this change in pressure affect this equilibrium system? Will the system remain at equilibrium if you change the pressure, or will the equilibrium, at the instant at which you change pressure, will the equilibrium be upset?
It'll stay the same because there's no change in moles.
What is that?
It'll stay the same because there's no change in moles.
No change in moles. Well, I agree there's no change in moles.
It could change if the water vapor goes to liquid water. If it's condensed, it'll change the pressure.
That's correct. Do you recognize that of the four components of this system, the one which exhibits the highest intermolecular attraction forces by far is water. And what are these intermolecular attraction forces to which I refer? Hydrogen bonds, you betcha. Much stronger than London force associations or dipole-dipole associations. But if you operate at a pressure which causes water molecules to coalesce, then you're going to upset this equilibrium. In fact, you don't even have to operate at a pressure which brings about condensation of water. If you operate at a pressure in which water molecules no longer behave ideally, why would extremely high pressure applied to this system cause water molecules to behave non-ideally? What does ideal behavior depend on? No intermolecular attractions. If there are no intermolecular attractions exhibited by any of the molecules in this system for each other, for like molecules of the same gas, or for any other molecules in the system, then you have ideal behavior. Because ideal behavior depends upon all the particles in the system behaving as if they're individual, in their behaving all by themselves. Did you hear about another? Did you learn about another system type which depends on this behavior in Chemistry 2045? Did you learn about colligative phenomena? What do colligative phenomena depend on?
Concentration of the solute.
Well, okay, but more to the point, number of particles in the system. Colligative phenomena are rather like physical phenomena rather than chemical phenomena. I'm not entirely sure that's true, but so far studies seem to indicate that it is true. The number of particles in the system depends upon how a system behaves colligatively, as opposed to their chemical nature. Now, question 1711. You can do the arithmetic. Well, imagine that all the gas molecules in the system are behaving ideally, which means they shall exhibit behavior which is describable by the ideal equation of state for gases, PV equals nRT. Temperature is 1218 K. Well, at this temperature, would you expect all these gases to behave ideally? Really, if water gas is going to behave ideally, then the rest of them will behave ideally. Is that correct? Sure. Hey, all these materials under normal laboratory conditions are all gases except water. Normal lab temperature condition about 25 centigrade. Or is 25 centigrade. Just a simple definition. So we all know what we're talking about when we say we're operating under normal lab conditions. A commonly considered arbitrary thermodynamic state. 1218 K. That's way above the normal boiling point temperature of water liquid. Which is what? What is the normal boiling point temperature of water liquid? What is it? What is it? 373 K. So if we operate with the system at about 374K, 375K, PV equals nRT won't work. You'll need van der Waals corrections and stuff like that. Did you talk about van der Waals corrections in 2045? Now then, 1719. An equilibrium system, which we're going to analyze in detail when we get to chapter 21 in the notes. An equilibrium reaction established by NO2 molecules coalescing, combining with each other to make N2O4 molecules. That equilibrium system is contained in this vessel. Question: is this equilibrium reaction as written? Means you read it left to right, as written. Is it exo? Is it maybe exo? Is it guaranteed exo? Is it endo? What say you? In terms of moles, 2 moles NO2. If they combine completely, we wind up with 1 mole of N2O4. Is that reaction as written guaranteed endo, guaranteed exo, or is it the case that we don't know and we need more information? Guaranteed endo. Guaranteed exo. Need more information. How many didn't vote? 5,000 points off quiz 1 for everybody who didn't vote. Hell, quiz 1's only going to be worth about 100 and something. You're really going to owe me one hell of a bunch. Because you didn't vote! Look at that reaction. Tell me, when you find a reaction is exo, which means as you run the reaction, the temperature of the system increases. If you find a reaction to be exo, what do you know about that reaction system beside the fact that it's heat liberating? What do you know about the component materials of the reaction system? Because that's the most important part of knowing whether or not a reaction is exo or endo.
They lose energy.
What is that?
They lose energy.
I want more.
The products are more stable, are lower energy state than the reactants.
That's correct. Why?
Well, you broke a double bond.
You broke a double bond.
Or resonance, so it's like between a bond and double bond. But
As NO2 molecules react in this system, do you think you're breaking any bonds in NO2?
no.
Yes or no? It's all right. Don't mind me picking on you. I just play it that way.
I was thinking the bond's broken.
Are bonds being broken as NO2 molecules react to become N2O4 molecules?
Yes.
No.
Energy is released as the two come together to create the rear molecule.
That's correct, but that was already stated. So what we're finding out is that from a bond strength standpoint, the product of this reaction is more stable than the reactants. That guarantees this reaction is what? Exo. Energy liberating. Exo. You didn't learn that in 2045. I know what the hell they did in 2045. They gave you a bunch of reaction equations and monkeyed around with Hess's law with no explanation of chemistry. Well, the hell with that. Now we're doing chemistry and nothing but chemistry. But the fact that you didn't get that in 2045 isn't your fault. We'll fix it. We're going to start fixing it right now. You see my directive here? Lewis structures for NO2 and N2O4. Come on, right now on your paper. Let's go. Lewis structures. What do you do first when you write a Lewis structure?
Out of the electrons.
Count the number of valence dots. Because if the picture you draw doesn't have the right number of valence dots, I don't give a damn what else you do, it can't be right. How many dots for NO2? How many? How many dots for NO2?
17.
17. An interesting molecule, wouldn't you say? Because it is a radical. What's radical mean?
It has one electron, that's okay.
At least one. A radical is a chemical species which does not have all its valence orbitals completely filled with electrons for those orbitals which contain electrons. One or more orbitals is half filled. That means it's got one or more unpaired electrons in its valence structure. Now in writing the Lewis structure, I'll tell you NO2 has one half-filled orbital. Come on, make the picture right now. If you count up the number of dots, what's the next step? Selection of? You're going to write this Lewis picture for NO2. You know the number of dots. What do you do now? You sketch the formula for the central atom, don't you? Come on. Believe me, whether or not you learn how to do Lewis structures in 2045 shall now become immaterial and irrelevant, because I'm going to see to it that you know how to do this stuff. Because structure is the most important property of any chemical species. So we got to get its structure. If we're going to get it anything for a chemical species, we got to get its structure. That was tough. And now what's next? What's next now, if we have a single central atom species, which is what NO2 is, we glue on the peripheral atoms with the minimum quantity of chemical glue. Oh boy, what a fancy sounding statement. What is the minimum quantity of chemical glue? A single bond. So let's glue on our peripheral oxygen atoms with single bonds. Then what's next? What's next is if we have an even electron species. Is NO2 an even electron species? What does even electron mean? Means the total number of valence electrons is an even number. Is 17 an even number? No. But if this was an even electron species, we would continue in constructing our Lewis picture by completing octets on all peripheral atoms, except for hydrogen. Remember that? Now then, regarding this octet rule, to what atoms in the periodic system does the octet rule apply absolutely, and under what conditions?
Lithium through
not lithium. You know what I'm doing now? I'm asking you if you learn what I told you to learn in Assignment 6, 2045 laboratory. Yeah, I'm a dirty rat. I expect that you did 2045 laboratory by learning what the hell was in the course.
The octet rule applies to every single four phosphorus.
Nope. I want to know the atoms to which the octet rule always applies and under what conditions. I'm listening.
goes to the P block.
Nope.
Any atom before phosphorus?
Nope. We don't know, do we? And you can't get this out of these dumb textbooks. They're not even good for door stops. That's why I kicked it out the door.
From carbon to silicon.
Nope, you got one of them right.
First two periods.
There's only 3 atoms, I'll give you that hint.
Carbon, nitrogen, and oxygen.
Yes! Now under what conditions? Carbon, nitrogen, and oxygen as component atoms of even electron species. See, that's it. Even electron comes in. That means a number which is uniformly divisible by 2. You know that. Those are the only 3 atoms to which this octet rule applies always. Carbon, nitrogen, and oxygen in even electron species. That's it. And no other atoms. This isn't even electron. Now tell me then, if we're going to complete octets for any of these atoms, will we complete the octets for oxygen or nitrogen? Preferentially. Why? More electric, good, all right. So here we go. Zip, 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 zip. One remaining electron, I'll put it there. You like this picture? Why not? Formal charge is lousy. Plus, as things stand, our picture shows the nitrogen atom with how many valence electrons? 5. Woo, that's terrible. Because nitrogen, too, is an atom of significant electronegativity. So how can we draw a better picture than this while adding electrons to the valence environment of nitrogen so it comes closer to 8?
Double bond on the oxygen.
Double bond on the oxygen. Well, I'm lazy. I don't want to walk way over there. So I'll take one of these non-bonding pairs and I'll advance it to bonding status. Now at this point, when you think you've got a Lewis structure or a Lewis picture, which is the best you can do, in what way do you constructively criticize your picture? Yeah, formal charge analysis. Come on, let's go. Formal charge analysis, quick. Time's up. Now take note. If I write this Lewis picture, like this, I will have 0 formal charge distribution. So we have somewhat of a quandary, don't we? Because based on formal charge distribution, this is the better Lewis picture. But based on the greater electronegativity of oxygen, which means oxygen will preferentially complete its octet, because in this picture, nitrogen has an octet like this oxygen, but this oxygen is deficient. What do you think prevails? This picture drawing business of formal charges, or the electronegativity of oxygen, which is a true real property of oxygen? Electronegativity of oxygen. Bingo! So, we now know this is the correct Lewis picture for NO2. How's the central nitrogen atom hybridized? Come on, let's go. What is it? sp2. What are the perfect sp2 bond angles? 120 degrees. sp2, perfect sp2. Take a circle, imagine it's a pie, not this kind of pie, apple pie, okay? Like a clock face. The central atom's at the center of the clock, where the hands pivot. Noon, 8, 4, let's connect those positions. And we get 120 degree bond angles, don't we? Do you think that this O-NO bond angle right here, you think this bond angle is 120 degrees? You think it's greater than 120 degrees? You think it's smaller than 120 degrees? Smaller. Is that what you said? On what basis? Well, I heard radical. One non-bonding electron. You think a non-bonding electron repels bonding electrons as effectively as a non-bonding electron pair? No. And here at the bond sites, we've got bond order which exceeds 1, don't we? So here bond pair repulsion can be significant, whereas non-bond electron bond pair repulsion won't be significant because you only got a single non-bonding electron. Do you think that keeps with the bond angle of this molecule, which is known to be 134 degrees? How about that? And now we've shown you a way, based on fundamental considerations, you can rationalize this. This Lewis picture shows you that you have a greater degree of bond pair repulsion than you do for a molecule which only has single bonds. and a smaller degree of non-bonding bonding repulsion because you only got one non-bonding electron. How about that? Nothing fancy about this. And it's stuff you should have did in 2045, but I bet you didn't. But you're doing it now because this is chemistry and we love it. Okay? Now we got the right Lewis picture for NO2. It tells us the non-bonding electron is on nitrogen. Now when that reaction occurs, you tell me what bond is produced. Because if you do it statistically, when NO2 molecules coalesce to become N2O4, you could expect an NN bond to form, an NO bond to form, or an OO bond to form. All are possible statistically. But now you know what bond forms. NN, period, and that's the bond that does form, and it's the only bond that forms when NO2 molecules coalesce and become colorless N2O4. Do you believe then if I tell you that this flask contains this system, that it's certainly got NO2 in it? Because you see the brown stuff? Do you think it's also got N2O4 in it? You remember this reaction is exo. Is that favoring reaction progress?
Yes.
You betcha it is. So do you think there's N2O4 molecules in here as well? Yeah. They're colorless. You can't see them if they're there. You're damn right they're in here. You know why they're in here? You know why both NO2 and N2O4 molecules are in here? Because equilibrium is the most stable thermodynamic state in which a reaction system can exist. Bingo! That's why it's in here. Because any NO2, N2O4 mixture is most stable when it's at equilibrium. Bingo! That's what's in here. That's what's in here. All right. And now more great fun. Back to nitrogen, hydrogen, ammonia mixture. Challenge problem 17.1. Page 1722. The tail end of chapter 17. Reminder right now before I forget. Starting tomorrow in discussion class, for your own benefit, you better have read the first 10 pages of chapter 18 carefully, and studied it carefully, and carefully. Okay? We shall imagine to look at the establishment of this equilibrium in reverse of the way we looked at it earlier on in chapter 17, where we had the nitrogen and hydrogen molecules as reactants and the ammonia molecule as product. Now we're considering ammonia molecules decomposing. And we are imagining that we've got this system contained in a piston cylinder gadget, which originally is at a volume of 1.0 liters. And we're studying this at the unique condition for which Kc has the simplest possible value, 1.0. Because again, I want you to focus on the chemistry and the method of solving this problem and not get lost with the arithmetic to the extent that we can protect you from that. Here's the equilibrium constant, chemically written. If initially, in this piston cylinder gadget, the equilibrium concentration of nitrogen is equal to the equilibrium concentration of hydrogen, which is equal to 1.0 that I forgot. Under these conditions, what's the equilibrium concentration of ammonia? 1.0. What else could it be? Okay? Under these conditions, how many moles of each system component do we have?
1 of each.
1.0 moles of each. Do you think we'd have to have a rather large piston cylinder gadget? Well, not if we're operating under extremely high pressure. But if we're operating under normal lab conditions, pressure 1 atmosphere, 3 moles of ideal gas at 25 degrees centigrade, what kind of volume we got? 3 moles of ideal gas at 25 centigrade. What kind of volume we got?
66 liters.
I'm listening.
Approximately 70 liters.
Bigger than that. Is 22.4 liters per mole ring a bell? That's the volume a mole of an ideal gas occupies at what temperature? 0 centigrade, 273 K. But if we're at 25 centigrade, we're at 298 K. So I'll take 22.4, multiply it by 3, and then operate on that value by what factor to get its volume at 298 K? What are you going to do with this, Boyle? Pardon me, Charles. Let's get this right. 298 over 273 times 3 times 22.4. You get about 75 liters. Well, we got a nice big damn piston cylinder here. Now comes the fun. We're going to take a hold on a handle on the piston. Shove it in. Until the volume of this system has been divided by 2. It's now 0.50 liters, at which point we will lock the piston in place. And here comes our job. Calculate the equilibrium concentrations for each system component. There it is. First, by applying pressure to this system, do we destroy the equilibrium?
Yes. Yes.
Absolutely. Because this doesn't have a balance of moles of gas right left, does it? If then the equilibrium is destroyed, and since we have not added or subtracted any materials to the system, or taken from the system, the reaction left to right for this system, or the reaction right to left for this system, has got to occur to get us back to equilibrium. Which of these reactions occurs? Right to left. That is correct. Did you read about this in the notes? Simply put, if you have an equilibrium involving gases, like this one, and there's not a mole balance of gases left-right, like this one. If we read it in terms of moles, we got 4 moles gas represented on the right, 2 moles gas represented on the left. If you apply pressure to such a system, you proceed from more moles to fewer moles. If you lower pressure on such a system, you proceed from fewer moles to more moles. Doesn't that make sense to you? If you got gases, wouldn't fewer moles of gas occupy a smaller volume more happily than more moles of gas? That's what's going on here. So we know, before we've done any arithmetic, this is what's happening to get us back to equilibrium. Now, we also know that this is the mole quantity of each gas component we started with. And now we've recognized that moles nitrogen will be reduced, moles hydrogen will be reduced, as moles ammonia become increased to get us back to equilibrium. Okay so far? Question. By what algebraic quantity shall we represent moles of ammonia increase? Directive. When you apply this algebra consideration to an equilibrium system, you let the equation for the reaction as it stands be your algebra guide. So I repeat, algebraically, how shall I represent moles of ammonia created to get us back to equilibrium? 2x. How about that? You see this too? X is what we don't know times 2. That's moles of ammonia made to get us back to equilibrium. So if we add that to what we started with, we'll have the total mole quantity of ammonia when we get back to equilibrium. Well, based on this, how much nitrogen will we have when equilibrium is reestablished? And how much hydrogen? How about that? And now, we no longer have the simplifying factor of mole quantity and molar concentrations being numerically equivalent, do we? Because we don't have a system volume of 1 liter anymore. So we've got to convert these to concentrations because our equilibrium constant expression is in molar concentrations. So we'll write this at EQ, okay? And there's what we got. Now, I don't like to fool around with fractions like this. So I'm going to, at least as I see it, simplify these concentrations by dividing the numerator of each term by the denominator of each term. Tell me, what do you do to something when you divide it by 0.50? You double it. Goody. So we'll write, for nitrogen, 2.0 minus 2x. For hydrogen, 2.0 minus 6x. And for ammonia, 1.0 plus 4x. Pardon me, 2.0 plus 4x. And now we'll write Kc, which is 1.0, and take a look at its algebraic equivalent. We got nitrogen, 2.0 minus 2x. We got hydrogen, 2.0 minus 6x quantity cubed. And in the denominator, we got 2.0 plus 4x quantity squared. Ha ha ha. Isn't this nice? Can you solve this with the quadratic formula? Can you solve this with any recipe you learned about in math class? Would you like to expand this and turn it into a 4th order polynomial and then monkey with it? Well, if you like torture and pain and agony, I suggest you do that. But if you'd like to learn how to solve it by thinking like a chemist, then I'm going to ask you to look at this expression and tell me which of these terms is smallest. Which term is smallest? 2.0 minus 6x, the hydrogen molarity at equilibrium. Now I'll ask you another question. In algebra class, equations like this can have true values for x which are negative. Can I get a legitimate solution for this problem where the value for x is such that 6x is bigger than 2.0? Can I have negative concentrations? Hell no! Chemistry. So tell me, what is the largest possible value that x can have while allowing each term in this expression to be non-zero, because if it's zero, the equilibrium doesn't exist, and positive? What's the largest value that x can have? What is x max? I'm listening. Can x be 0.34? No, because 6x then is bigger than 2.0. So here's x max. Can x max be a number which has more sig figs than 0.33? How many sig figs we got in any of these values? 2. All right, so there's x max. And x min is this. Now, there's another consideration which you were asked to read about in Chem Notes 2 that relates to this problem. This consideration is represented algebraically by the fancy Q, by this fancy Q symbol. What's that mean? Reaction quotient. Did you read about reaction quotient in the notes? Good. So, I'm going to finish this one on Wednesday. The discussion, folks, tomorrow will proceed into Chapter 18. That's why I told you to do what I told you to do about going with Chapter 18. Question? Based on this information, what do we do to solve this? What we do to solve this is to pay attention to the information which you see in section 1711. So take a look at that, and we'll proceed with the solution of this top of the class on Wednesday.